Okay, this is where we left off with the gas laws. We learned the Boyle's law, Charles' law, and Avogadro's law, and I emphasized that you just have changing variables when the other ones are constant. The variables in question when analyzing a gas are your pressure, volume, your temperature, and the number of moles. The Boyle's law is volume and pressure. Charles' law is volume and temperature, and Avogadro's law is volume and number of moles. And so when you're analyzing any two of those, the other ones have to be held constant. What the ideal gas law does is it combines all of those. And the ideal gas law is V is equal to R over Tn. If you substitute in one law into the next, this is what you get. You get this PV is equal to nRT, which is the ideal gas law. And so what this does is it introduces another constant, because again, we talked about these being proportions. In order to make them equalities, we needed to introduce a constant K, B, and A for each respective law. Well, for the universal gas law, we combine those constants into a constant R. And that constant is equivalent to this value here, 0.206 liter atmospheres per mole K. And if you look at on your AP appendix, it's going to be listed there for you. And so it's also probably a good idea to program this one in your calculator as well as memorize it. So for all gas problems, so once you know this law for all gas problems, you're either plugging right into this equation or you're using this equation to construct another one. And so you don't need to memorize Boyle's, Charles, and Avogadro's, because what you could do is, so let's say that, actually let's just pull a sample from above. So here is Avogadro's law. And so I could do this problem. So it says this is Avogadro's law. This is the one that we're going to use right here. But what I could do instead is I could just set it up like PV is equal to nRT. So use my universal gas law. And then I analyze this and say, okay, what is changing and what's being held constant? So I'm going from 12.2 liters. And let's see here. I guess this is not a very good example. Let me choose a different example. That example would work, but to emphasize my point, it's going to be best to use a different one. Okay, so let's use this example. And so I have PV is equal to nRT. So I look at this problem and I say, okay, I have my temperature is going from 15 to 38. It's at 1 atmosphere, so that's not changing because it says what volume will this gas occupy at this temperature in 1 atmosphere. So atmosphere 1 atmosphere to 1 atmosphere, there's no change in pressure. So the pressure is being held constant. So I'm just going to, I guess I will highlight that, or maybe I'll mark it with an X above it. So let's do this. I'm going to mark my pressure as being constant. So that's not changing. So I put an X there. Volume, that's what I'm solving for. So volume is changing. Okay. Sample of gas has a volume. What volume will the same gas? Okay. So we're implying it's the same gas. So therefore the number of moles must also be constant. I don't know why it's doing that. Okay, there we go. So pressure is constant, moles are constant. Obviously our constant R, our universal gas constant. So we're dealing with just the volume and the temperature changing here. And so what I could do is I could just rearrange this equation to isolate the constants. And so I'm going to divide both sides by V. So V's obviously cross off on the left side. And then I can then move over the N and R by dividing N and R on both sides. I'm going to put N and R on the other side as well. And so on the right side I get N and R crossing off. And so what I ultimately get is P divided by N R is equal to P over V. And so what I've done is I've taken things that are constant and I grouped them together, and then I took things that are changing, the temperature and the volume, and I grouped them together on one side. And so what I could do is I can combine all three of these things that aren't changing into one constant. And so that's kind of like the same thing as saying that T over V is equal to a constant. And so if T over V is equal to a constant in one case, it will also be equal to that same constant in any other case. And so I have T over V is equal to T over V, which is Charles's law. And so I could then use this as my equation where I'm plugging in my two temperatures, 15 and 38, and then 15 matches up with 2.58. So 15 and 2.58, remember we need to convert temperatures to Kelvin. So 15 plus 273 is plugging in for this T, 2.58 is plugging in for this V, 38 plus 273 is plugging in for this T, and I'm solving for this V. Okay, so I was able to construct Charles's equation without having to memorize it. So I could just use the ideal gas law for everything. And obviously this is all kind of long and drawn out as I took the time to explain it. But once you've done this a couple times, it's very simple. And so why bother trying to memorize all three of these equations, Boyle's, Charles, and Avogadro's? You could just always use the ideal gas law and rearrange it as necessary. So for any time you have a gas system that is changing with the other, so if you have two things changing in a gas system while the other two variables are held constant, you could do that. Okay, figure out what's constant, isolate them all on one side, clump them together in one big constant, and then construct your change in equation. Another way you could use the ideal gas law is if you have three of the four variables, you could plug in 3. So if you have P, V, and N, you could solve for T. If you have V, N, and T, you could solve for P, so on and so forth. The only caveat there is you need to make sure that the units that you're plugging into the equation match the units for the constant that you're using. So if I'm using this constant 0.08206, I need to make sure my volume's in liters, I need to make sure my pressures in atmospheres, I need to make sure my temperature's in Kelvin. Okay, and my moles are in moles and not grams or millimoles or something weird like that. Okay, and so you just use unit conversion for every instance where the units do not match up. Okay, and so once they all match up, you can plug them all in and solve for the unknown. So those are, that will cover nearly every ideal gas. That'll cover every rendition of a gas problem you're going to encounter, is using the ideal gas law to construct one of those simpler gas laws, or using the ideal gas law as is in a situation where you know 3 of the 4 variables. You will run into gas stoichiometry. Gas stoichiometry works with normal stoichiometry, except for the only thing is that you have this conversion that 1 mole of any gas is going to be equal to 22.4 liters at STP. And STP is standard temp and pressure. And standard temperature is 0 degrees Celsius, so it's actually colder than room temperature. So a lot of students get confused and they'll think that STP is 25 degrees Celsius, which is room temperature, but in fact it's actually 0 degrees Celsius. So it's 0 degrees Celsius, 273 K, and then the pressure of 1 atmosphere. Okay. And so as long as a gas is at that temperature, or at that, this is supposed to be K, as long as a gas is at that temperature and at that pressure, you can use this equality in a unit conversion, which will fit in any stoichiometry problem. So if I want to go from moles to liters or liters to moles, provided that I'm at STP, I can use that in my stoichiometry problem. So that's the molar volume of an ideal gas. You'll also run into a version of the ideal gas law where they will take N, so they'll take, PV is equal to NRT, and then they will take the N and they'll substitute it. So they'll take PV is equal to, and then in parentheses, the mass divided by the molar mass times RT. And what that allows you to do is if I divide density on both sides, and then you could see them constructing the equation up here. So you could see they swapped in the mass over molar mass, and molar mass ends up in the denominator, and you could see they get M over V. M over V is density, and so they wind up with this rendition of the ideal gas law. And so if you were given a density and it's a gas problem, you're probably using just this rendition. And so they have, if you look on your, if you look at your AP appendix, there's going to be this version of the ideal gas law or some rendition of it on there. And so the last section that we weren't able to cover yesterday is Dalton's law of partial pressures, and what that is just pressures of gases are additive. And you'll come across some problems in your problem set. You'll get some practice with these, but one of the trickier ones is whenever you're collecting a gas over water. So here's an example of a setup where you collect a gas over water. So we have this potassium chlorate or manganese dioxide, has a lot of oxygen. When heated, it releases oxygen gas, and so you could bubble that through water and collect it. However, since you're bubbling it through water, as you collect it, you also have water vapor in there. So if you have a problem and you're trying to determine the pressure of this gas in here, you have to take that into consideration. And so if you look at this example here, there's a sample of solid potassium chlorate, KClO3, was heated in a test tube and decomposed by the following reaction. So you can see it produces the oxygen. The oxygen produced was collected by displacement of water at 22 degrees Celsius and a total pressure of 754. And so note, this is the total pressure. And so since we have the temperature of the water and we have the total pressure, what we could do is they give you the partial pressure of the water, 21 torr, and you could just look and say, okay, well, if the total pressure is 754 and I subtract out the 21, I could then determine the pressure of the oxygen, okay? And then when you go to use that in the ideal gas law, you'll be using the correct pressure rather than the total pressure. And so when you go to back calculate for the mass of the KClO3 used, you'd use the ideal gas law, and you'd be very specific and plug in the pressure of the oxygen to match with the moles of the oxygen that you're solving for. Once you solve for the moles of oxygen, you could then convert that to the moles of the KClO3. Okay, and so you need to subtract out the pressure of the water every time you're collecting gas over water. Okay, because there's going to be, you have to realize, and this will almost always come up on an AP test, you have to realize if a gas is collected over water, the pressure of the water has to be subtracted out. Okay, and the partial pressure of the water is dependent on the temperature, and so it will either be given in a table or they will explicitly tell you the pressure of the water, or maybe you'll be calculating for the pressure of the water. Okay, and so that is one type of problem that's going to come up with Dalton's law almost always. Okay, and so that's enough to bring us into the next lesson, 5-6. So I will stop there. Make sure that we are working on our problem sets, and if you have any specific questions, you can email me.